Bismillah ar-Rahman ar-Rahim. Welcome to the last tutorial or the video class, which will cover chapter 28. This is the chapter on mainly the calculating the magnetic field. First, we will calculate the magnetic field due to a point charge, a moving point charge. And then after that we'll calculate the magnetic field due to current carrying conductor, and that current carrying conductor could be in several forms, either a line, a straight line, or some coil, either in the form of a solenoid or a toroid. So the objectives, as you can see here, the objectives of this chapter is to first determine the magnetic field produced by a moving charge, and again we do the same thing for a current carrying conductor, and also we would like to calculate the magnetic field with straight line and so forth. And another important topic, which is calculating the magnetic force between two or three or more current carrying wires. This is important because once you create, or once there is a current flowing in a conductor, then that conductor will produce a magnetic field. If the magnetic field, if there is a charge or a current near the magnetic field, then there will be a force produced. Well, that's how important this is. And of course, then we'll finally use the Amperes law to calculate the magnetic field. So the magnetic field will be determined two ways. One is directly using integration or calculus, and the second approach is using Ampere's law, which is straightforward, similar to what we did in electrostatics, where we first calculated the electric field using straight or directly using calculus, and then we used what we called at that time Gauss's law to calculate the electrostatic field due to a charge that has some symmetry. Okay, so the first thing that we wanted to look at is what is the magnetic field produced by a moving charge. So if you look here, I have a charge that is moving with some speed v, and that charge is produces a magnetic field b, and the direction of the magnetic at some distance r, and the direction of the magnetic field is determined by the right hand rule. So I place my thumb along the velocity, and then I curl my fingers counterclockwise. So my thumb will be, let me just see if we can get the colors. Okay, so my thumb will be this way, and then I curl my fingers this way. These are so counterclockwise. Therefore, the magnetic field at this point is into the page, and if I am looking here somewhere at some point here, the magnetic field will be out of the page, simply just because of the this direction. Okay, so the way we wanted to find this magnetic field here, the way we'll do that is by using something called the Biot-Savart law. And the Biot-Savart law is defined as defines the magnetic field at some point r away from the moving charge. This is a constant. Mu naught is the permeability, which we defined in the first class, and it is related, and the permeability and the permittivity is actually related in such a way that you can get the speed of light by simply taking 1 over the square root of the permeability times the permittivity under the square root of free space. Okay, if you do that in free space, then you get the speed of light. The product 1 over the square root of the product gives you the speed of light. That's a very important finding, which becomes very important later on if you were taking applied electromagnetism. Then this becomes very important to find the relationship between the magnetic and electrostatic field. So anyway, so the electrostatic field, the magnetostatic field B, and when I say magnetostatic field is that we are producing a uniform magnetic field. So it's simply the charge multiplied by the speed of the charge. Okay, so because the charge is moving at some speed, and the magnitude of the charge, and we are taking the cross product of the unit vector r hat divided by r squared. So r squared is simply the distance between the square of the distance between the position of the charge and the point of interest. R hat is simply a unit vector that shows us or gives us the direction of r. So this will be my r hat. Okay, that's r hat, and this of course will be different if you take if the charge was moving downwards, because then my thumb will be here, and then this way. Okay, so I have to remember, I have to go this way. Okay, and then therefore this is wrong, and remember, I have to curl all the time. I have to curl curl my right hand. So this will give me the field out of the page, and in this region here is into the page. Okay, so the other thing that I wanted to look at, or we wanted to look at before we go on, is the idea here is that the magnetic field, due to this moving charge, is actually depends on the distance away from the moving charge. So this is symbol actually just indicates the charge moving into the plane. So this is the charge that's moving into the plane. So this is actually Q, and we see that the magnetic field varies, as you can see, 1 over r squared. So as you get away from the charge, the magnetic field becomes less and less as a function of 1 over r squared. Okay, that's very important. All right, so let's move on. The other thing that we need to know, and this is very important calculation, is to find the direction of the magnetic field. The way we find the direction of the magnetic field is by doing or executing the cross product between the speed and r hat. And the way we do that is by simply, doing the matrices. And those of you who did not take algebra before, you can do that very easily by simply, for example, here QV for this settings here. For this setting, I know that V is along Y. If I take this to be Y, and this is X. Okay, so my QV in this case, my Q times V is along Y, so this is X is 0, Y, and Z or J hat, and then I repeat the first two. Okay, and my R hat in this case is along along X, so that will be I hat 0, 0, and then I repeat the first two, and then I do the cross product directly. This will give me 0, and this will give me again 0, and this will give me minus QV. The advantage of doing it this way is that you don't have to worry about assigning a minus sign here. This is done directly. So just a straightforward, solving the matrix. Okay, so let's move on. Let's do the first example. We have two protons. Okay, they're both moving at the shown direction. So the top proton is moving this way, and the bottom proton moves this way. So find the electrostatic and the magnetostatic force at this point here, at this point when they cross each other. Okay, so he wants you to find the electrostatic force and the magnetostatic force. Okay, the electrostatic force is straightforward, because what we have to do is simply F is equal to QE, and E is simply Q divided by r squared in the direction, because this is positive and this is positive, so it will be upwards, okay, along Y. So the electrostatic force is simply Q, right, multiplied by the electrostatic field, and the electrostatic field is Q divided by r squared, or KQ over r squared, and the direction of the electrostatic force is up because these two charges are positive. Okay, so I found the electrostatic force. To find the magnetostatic force, I first have to find the magnetic field at this point here, and then after I find the magnetic field, I can calculate the electrostatic, the magnetic force. Well, the magnetic field at this point will be due to this charge. Okay, and I have to do it using this formula, which we just took a few minutes ago, or talked about a few minutes ago, where the magnetostatic, or the magnetic field, is actually equal to some constant multiply the QV, the moving charge. This is the charge that is going to give me the magnetic field. Cross r hat, and this is r hat, and r square is this distance. Okay, so what does that mean? That means I have to cross v cross r hat. R hat is along y hat, or along j hat, and v is along positive I, so positive I hat. So if I do that, I have QV along the x, that's this, and then 0, 0, and then I repeat the first two, and the r hat is along j hat, so 0, 1, 0, and then I repeat the first two. When I do my cross product, or I do this will give me 0, and the j hat again will give me 0, and the k hat will give me qvx. So the result of the magnetic field will be simply qvx, and of course this divided by r square, and it's along k hat, and that's what we have. So so my magnetic field will be this simply qvx over r square on k hat. And to calculate the magnetic force Fb, then I have to do qv, this v here, crossed with B, which is produced by the lower proton. So that means I have to cross minus I hat with K hat. Okay, with K hat is the coming from the magnetic field. If I do that, so remember this is minus, right? So minus QVX 0, 0 minus QVX 0, and then 0, 0 B, because it's along K hat. The magnetic field that we found from the due to the lower charge is along K hat, and then from here I get this to be 0 for the I hat. The J hat gives me 0 minus minus. This will give me BQVX. And remember, B we calculated from here, and then 0. So the resultant force, or sorry, the magnetic force is also along the I hat. Sorry, the J hat. So what we've done, we've calculated the electrostatic force QE, and then we found it to be equal to this along the J hat direction, and then we calculated the electric field, the magnetic field, which we found it to be, this is the magnetic field due to the lower charge, to the bottom charge. And then from there we calculated the magnetic force on the upper charge, which is QV of the upper charge, which is minus I hat, and then cross with this K hat, and then if we do the cross product, we get again the magnetic forces along the J hat, the J direction, the J hat direction. And if I want to calculate the net force, is equal to F electrostatic plus F magnetostatic. And then when I do the sum, all I have to do is just do this. This is for the proton, and the distance is given. This is all given, and the only thing that I don't have is well, actually, I should be given the velocity. Okay, and that's it. All right. So just before I leave this, remember we had in the quiz, we had a question where one of these guys is an electron. Okay, so what does that happen if one of these guys is an electron? Then, well, the first thing, this is going to be different. So the electrostatic force will be down, and also if this is an electron, the force, so the magnetic field produced by this will be in the other direction, which is minus K hat. Okay, and then you just carry on. It's a good exercise if you wanted to do it, and you guys have the question now. Okay, now let's look at the Biot-Savart law for a current carrying conductor. So instead of a charge, we're looking at something like this, where I have a current, a conductor that is with current flowing in the conductor. So the way we find the magnetic field is simply replacing QV with IL, which we know how to do, or I showed you how to do it in class, derived it as QV is equal to IL. Using the definition of the the current, and current is simply Q over T, okay, or the flow of charges per unit time. Okay, now, and if I am looking, of course, at some wire, then the way I do it is by simply breaking this wire into small segments, dB, so small segments of dl, and I apply this to give me the magnetic field, the infinitesimal magnetic field. And then, of course, if I integrate over the length of the wire, then I get the magnetic field due to the wire. So this is called the Biot-Savart law. Now the idea here, be careful, is that if you look at this, where you curl your fingers around on with your thumb up, you see that the magnetic field in here is into the page, as you can see with the hand here, while at this point is out the page. The way to get out of this is that it's tangential to the loop, or at any point on the loop where the distance is located, or where the point is located. So make sure you do not mix it. So if I am here, if I am at this point here, the direction of the magnetic field will be this way. If I am at this point here, the direction of the magnetic field will be this way, and so on. Okay, so let's look at the application of Biot-Savart law. And the first thing we want to do is we want to look at calculate the magnetic field due to some finite conductor in the form of a wire that has a length of 2a. We've done this math, all of these mathematical steps in class, but remember, we start with the Biot-Savart law, and IL cross R hat, so that will be I dl, or sorry, dl sine phi, and sine phi is the angle between I dl. And if you look at that, this is the same, sine of this angle is the same as sine of this angle. So, and I've shown you that here, okay? And so if you do that, then the sine of this angle will be simply x over that, x over this. If you put everything together and you integrate using this standard integral formula, then you get the magnetic field at this point. First of all, it's as you can see, it's into the page using your right hand rule, and this is what it looks like. The detailed mathematical details are here. If you go from A to minus A to A, then you get the magnetic field in this form. And you also can simply, by taking A out, A, of course, A squared, so that will be A, the A's will cancel, and then you get 1 over, so x squared over A, simply for the reason that if we wanted to, if A goes to infinity, this goes to 0, so 1 over infinity is equal to 0, and then we get this formula for the magnetic field due to a current carrying conductor. Okay, so let's summarize this. So the magnetic field B at some point P located at some distance away from the wire. There are two ways. One, if the wire is finite, so it has a finite length 2a, then the magnetic field is defined this way. So you have 2a and then the length of the wire, and then divided by half of the wire, half of the length of the wire, and x squared, which is x is the distance from the wire. However, if the wire is infinite, then so x over infinity goes to 0, and then this goes out and you have 1 over x, and this is the one that is most important formula. So B, the magnetic field due to a long or infinite current carrying conductor in the form of a wire, it's simply equal to this formula, 1 over x. So the magnetic field will go something like this. So if this is just as you get away from the wire, so this is the magnetic field B, right? And this is R or X. So as you get away from X this way or this way, the magnetic field comes down as 1 over X. Okay? So this is very important summary, and actually I think I mentioned this several times. This is very important formula, and we will use it a lot. Okay, the first question, or the first example, is to calculate the, you have two infinite wires. So this guy is into the page. This is a wire going into the page, carrying current going into the page. And this is a wire that is carrying current out of the page. So this is wire 1, wire 2. They are parallel. It's something like this. And just get the pen. It's something like this. Yeah. So parallel, but they are into the page. And what does he want? He wants you to calculate the magnetic field at this point in between, at some point here outside, and at some point here outside. outside. So in between, outside on this region, and outside on that region. Point P1, P2, and P3. So the way we do that, if let's say if we come to point 1, we will have two magnetic fields, or two contributions to the total magnetic field. One contribution is due to this wire. So remember, since this is out of the page, so if I curl my fingers, so the magnetic field will be this way, right? And this guy is into the page. That means if I curl my fingers, the magnetic field will be this way. Now this guy here, remember, this is out of the page. That means the magnetic field is this way, and this is into the page, right? So the magnetic field will be this way, and so forth. You can do that, and I think I have them here. Okay, sorry, this is wrong here. So if you're at this point here, you curl your finger. This is wire 1. Let me just write them down so that we don't lose them. So this is out of the page, and this is into the page. So if I do the magnetic field here, this is out, right? Out of the page. That means this is my magnetic field. Out of the page. That means I curl this way, so that will give me this magnetic field. And this one I curl, because it's out of the page, I curl this way. Okay, so that will give me this magnetic field. Okay, this is the direction of the magnetic field. If you look at this point here, okay, so for this one, I'm gonna remember out, so I curl this way, and that will give me this magnetic field. And this one is in, and I curl this way, and this will give me this magnetic field here. So in this point here, they both add, while in this point and this point here, actually at this point too, they subtract. Because if you look at this one, for wire 2, which is again into the page, so into the page, that means you curl this way, and this will give you this guy here, B2, and this one you curl this way, and then that will give you this one, this wire right here. Okay, so what does that mean? That means in here they subtract. For at point P1 they subtract. For point P2 they add, and for point P3 they subtract again. Okay, except here it's B2 minus B1, and in here B1 plus B2, and here B1 minus B2, and I'm taking upwards is positive. Okay, so if we do that, we have the solution here. So at point P1, that means I'm going to get the one that is going to be subtracted is B1. Okay, B due to wire 1, and the distance, remember, if the distance from here to here is 3D, so the distance here, and this is D, so this will be 2D. So 1, and of course the magnetic field is mu naught over 2 pi 1 over x, right? The magnetic field B, right, is equal to mu naught over this whole thing, and then we have 1 over x. Okay, and x is the distance, so there is this number here that we have to keep in mind. So as I said, the B1 at this point is negative 1 over 2D, right? From here to here is 2D, this is 3, minus D is 2D, and from here to here, that is 3D plus D, so that's 4D, and if you do that, then that's what you get. Similarly, B at point P2, this is point P2, so these guys will add, and the distances, as you can see, both of them are D, so it's simply you add them up, and then you get that. And at P3, okay, so which one of them is going to be, B1 is going to be positive, so B due to wire 1, which is you have 2D plus 1 is 3D, and then this guy here is 2D minus D is D, so this will be subtracted. And then if you subtract these guys, that's what you get. So if you look at the magnetic field at P1, okay, it's negative. That's the total magnetic field here, this point here. That's the total magnetic field. If you look at the magnetic field at P2, is it's big, right? And it has it's positive. If you look at the magnetic field, the total magnetic field at P3 is greater than this, and it's down. Okay. So that's the and remember, if you look at the strength of the magnetic field, you see that because of the fact there's two of them, the magnetic field here gets stronger, 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 but it gets weaker, 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 and you go away from the wires from the outside. Okay, that's it. Another example, which again we've done in the class, is something like this, where you have two wires. Okay, each one of them is going in this direction, and I2 is this direction, and he wants you to find the magnetic field at this point. Again, using the formula, mu B is equal to mu naught I divided by 2 pi multiplied by 1 over x. In this case, x here is 4 centimeters, so it's 0.04, and in this case here is 0.06 meters, and here is 0.04 meters. The question is the direction. So for this one, my finger is this way, right? And this is my thumb. My thumb is this way, and my thumb is this way, and I have to curl, right, so that this is out. So the electric field, so the magnetic field due to this guy is out of the page. Out is positive. We'll consider out as positive and in is negative. However, for this one, okay, so it's the magnetic field is it's into the page, because you curl this way, right, into the page. So this will produce into the page, and this will produce a magnetic field out of the page. So the B due to wire 1, right, is negative k, that's into the page, and B due to wire 2 will be out of the page, as we saw. When you add these two guys together, everything is the same. The only thing that so you pull this out, mu over I forgot the I, because the i's are the same, so I forgot I here. There should be an I1 is equal to I2. Both of them, each one of them carries current 2. I canceled the 2 with here. Sorry, I did not forget it. So 2 cancel this one, and that's where the 2 disappears. And then from there you can calculate the total magnetic field, and whether it's positive or negative, it will give you the whether it's into the page or out of the page. If it is into the page, then the answer is negative. If the answer is positive, then it's out of the page. Okay, let's look at this example, which is a little bit, it's one of the famous examples. What we wanted to do here, we have a long wire. Again, long wire means infinite length, so that means the magnetic field is B equals to mu naught over 2 pi, mu naught I over 2 pi 1 over x. And a particle has a charge that C is moving parallel to the wire. So the charge is moving parallel to the wire this way, and at the distance, so he gave you the distance from there, that's my x. And he gave you the speed of the wire. Determine the magnitude and the direction of the magnetic force on the particle. Okay, so we need to know the force. By the way, this is something that shown in the book, that B, V, and F are all perpendicular to each other. So this is perpendicular to this one is perpendicular to one, this one is perpendicular to it. And you can actually use your right hand. So if you draw your right hand here, your fingers are always pointing along the direction of B, and your thumb is directed along V, and your palm, the direction of your palm, is directed along F. So this is if you draw your hand something like this. Okay, these are your fingers. Okay, so so your fingers will be directed along B, right? And your thumb will be directed along V, and the palm, the direction of the inner of the palm, your hand will give you the direction of F. So that's general, just so that you know, and it's explained in the book, even though I'm not very fond of this, because I want people to do it using the cross product. But anyways, but that's what the book uses, or that's what people are accustomed to using. All right, so let's do that. I mean, the best way of doing that by simply simplifying this, taking this point here, where I is this is the direction of the current, and at some point here, B is into the page. So that's using my right hand. So my right hand rule. This is my thumb, and then I curl this way. So B is into the page, and that's V. So if I take this to be my X, Y, Z, so I is along Z. right? And B is along minus X here, minus I hat, and V is parallel, so it's along, again, it's along Z hat. So let's do that. The first thing that I need to find is B. Okay, so B in this case, as I said, it's along this direction here, into the page. Into the page is minus I hat, and of course it's mu naught I over 2 pi 1 over L. That's the direction of this. That's my magnetic field. And I can definitely do the cross product now of B, which I know it's minus I hat, and I know what V is, the direction of V in this case is Z hat. So I can do remember these, X, Y, Z, all right? So it's along Z, and then X, Y, and then this guy is minus I hat, so B minus B, 0, 0, minus B, 0, and B is this number here. That's what B. So if I do the cross product, this is going to give me 0 for the I hat, and this is going to give me QV minus B, okay, and 0 for the J hat, and and 0 of course for the K hat. So the cross product, the force, is actually, as we saw it here, as we predicted here, it's going to be minus I hat, which is according to this guy here. So minus J hat, because that's my Y in here. So if I do the cross product, I finish that, then that would be my answer here. So again, this is very straightforward, but you just need to work at it and make sure you know what the directions and cross products and all of these things work out. The force is directed towards the center at all times. What does this mean? That means the motion of the charge will be along some uniform circular path. Uniform because the velocity is constant, and if the velocity is constant, that means the acceleration is uniform, and that's what they call the uniform circular motion with constant. That means the speed is constant. That's all it means. The tangential speed is constant. All right, this is another way of doing this. Is what I said here earlier. So this is B, and this is V, and the direction of your palm is into the. So that's something that you can do this straightforward with QVB sine theta, but this is provided that you know where the angles are and so forth. So the angle here in this case is 90, and sine 90 is 1, so that's what you get for B, and then you multiply the QV, and the problem is solved. You can do this straightforward, but provided that you know the directions. And oftentimes, they will ask you to first calculate the magnetic field and then calculate the magnetic force. Okay, the second thing that we wanted to do, or the next thing that we wanted to do, we wanted to look at the force between two current carrying conductors. So if I have a current here, a conductor that is carrying some current, and another conductor carrying some current, we know from the example that we just did that there will be some force on any of the wires. So the wires will exert forces on each other. What we wanted to do, we wanted to see what is this force look like, okay? And we can do that by simply calculating the force of 1 on 2, and we know the force 2 on 1 will be same but opposite direction to that. So the way to do that is by simply I1, for example, I want the force on 2, then it will be I2 L2 multiplied by the magnetic field produced by this guy by 1 on 2. We've done this in class very well, and I'm sure you can follow that here, and I don't want to spend a lot of time on this, but the conclusion is the following. Where is this? Yeah. The conclusion is as follows, that the force of F1 and 2 is simply defined as I1, I2, L is the length of the wire, and I1 is the current in conductor 1, and I2 is current in conductor 2, and then you have this constant that is with us all the time, and this is the D is the distance between these two, and this is coming from the magnetic field, okay? And oftentimes you see that people wanted to calculate the force per unit length. So all you need to do is divide by L, and then you get the force per unit length this way. Now you see from this diagram, and this is something that we've done in detail in class, that if the direction of the current is parallel, the currents is parallel, then the force ends up to be attractive. If the direction of the currents is opposite or anti-parallel, then the force is repulsive. Okay, so that's something that you should be aware of. And there are some things that you have for this formula to be correct. First of all, the wires have to be parallel or anti-parallel, and I must be constant in the wires, and the wire has to be of infinite length. So we do not have, or actually it doesn't have to be infinite length in a sense, but they have to be at least the length is known for one of the wires because you can't have this infinite. And of course you can calculate this for let's say something 1 meter. If you have two wires, infinite wires, 1 meter length, then you can calculate from there the force produced on each other. All right, so we can calculate, for example, here what's the current if the currents produced with the wire is the same direction, opposite direction, the force is repulsive. An example here, if I have two current carrying conductors, and one of them is they both have the same magnitude current, and the distance between them is 4.5 millimeter, then the force produced by these two is repulsive, as we said. If you look back to the first, and so if the currents are parallel, they attract, and if they are anti-parallel, this is anti-parallel, not unti-parallel. Sorry, there's an A here. So, okay, so if they are, and they repel if they are anti-parallel. So in this case, in this case, because they are anti-parallel, so they repel each other, and the force is as defined by this formula here. It's simply I1 I2, which is the same, so I squared, and mu over 2 pi, and the distance between them, and 1 over the distance between them. Okay, so that's the solution for this question. This is another question that is very famous question, and what does it say? That you have a wire that is carrying some current, 15 amps, and then there is a loop, a rectangular loop next to it. And what is he wants you? He wants you to find, calculate the net force produced by the rectangular conductor on the wire, if the coil, this. So what does this mean? That means I have to find the magnetic field due to this conductor on at this point, and once I do that, that's the magnetic field, right? And then I just have I, and the length will be this length, because that's the effective length, is 30 centimeters. Now, one way of doing this is by splitting this rectangular loop into 4 sides. So side 1, side 2, side 3, side 4. But I have to know that the magnetic field on due to these guys is 0, simply because if you look at the magnetic field here and you use your right hand rule, so this will in this direction, or it's tangential in this direction. So the angle between these two guys is 0, and the sine of the angle, it will be 0. So there will be no contribution from these two guys, and this is always true. So there will be no contribution. B to this side, due to this side, and B due to this side is 0. So what does that mean? That means it leaves me with the contribution of this side on the long wire, and the contribution of this side on the long wire. So what does that mean? That means these two guys are anti-parallel, so they will repel each other. So the force will be downwards. Okay, and these two will attract each other. So this one and this one will attract each other, and so there will be the direction of the force will be this way. This way, and this will be this way. So for the parallel sides, I'm going to call this guy, and this guy is the parallel sides. The force of side 1 for the parallel. For the parallel side, that's these two guys. For side 1, this is side 1, which is repulsive, because these two guys are different. So all I have to do, mu I1 I2 L divided, the only thing that I need to worry about is 1 over D, which in this case is 0.075. I have to do it in meters. And then the attractive force, which is these two guys, attractive, I'm going to, repulsive is negative and attractive is positive. So this will be simply that. Just again, the only difference is the distance. Now you add 10 centimeters, so this will be 17.5, so it will be 0.175. And then I add the forces, and that's what I get. You see that it's less than 0 if you do the math. You see that less than 0, negative, meaning negative, which means that the repulsion, because I define the repulsion to be negative. Okay, that's again as one of the famous examples that usually they ask it as conceptual questions. Do you think it's attractive or repulsive? So you have to know how to do it conceptually or numerically. Another example where we have two wires. One of them is carrying current in, and this guy is carrying current out, so they are parallel to each other, right? And we want to find the magnetic field at this point here. Now again, we do it the same way. If you look at this, if you use your right hand rule by just simply looking at the direction of the field. So if here it's into the page, so that means I have to do this way. So at this point, the magnetic field is this way, tangential, because remember this is a sort of a circle here. And this one is out of the page. Okay, out of the page, that means the magnetic field will be this way as the direction. So this will be B2 and this will be B1. One way of doing that is you first find the magnitude of each of these two guys, and then use that to find the this angle, and then because of the way it's set, it's 45. So whatever angle you get, you add to it 45, and that will be your direction angle, which is usually measured with respect to x. I've done it the long way. So what I've done, I've just calculated first B1, B2, and then I found the components, the x component B1, the y component B2, and the y component of B1 and x component of B2, the y component of B2, and then I've calculated that. So I first calculated the magnitude of B1 and B2. Okay, so this is distance R, so it's something using he told me that they are infinite wires. And then I've calculated B1x, B1y, B2x, B2y, because the angles are all 45. Okay, and knowing that B cosine 45 is D over, I can calculate the angle here. I can calculate the angle sine 45, and from there I can find R. R is simply if you do this, right, and D over 2. And this is R, so from here you can find the relationship between R and D, and then you can find the B1x and B1y, and from there you can find the total magnetic field. So the total magnetic field of the magnitude of the magnetic field is equal to, this is the net magnetic field here, and this is the magnitude of the magnetic field, and this is the tangent alpha, and alpha in this case is actually this angle here. That's my alpha, okay, which is the angle with respect to the x-axis. All right, so again, this is a little bit long, but easy to do. Now another example where we have two parallel lines, and they are separated by a distance 2d, and they carry equal currents opposite directions, so there is a repulsion here. Find Bx at the point A. So he's not looking for the force, he's looking for the magnetic field at this point here. So I know that the magnetic field in this case, because this is down, so when I curl my finger, this will be B at this point here will be N, okay, into the page. And for this one, it will be again into the page. So the magnetic field will add, okay. So the only thing that I have to worry about, remember they both add because they both are into the page. Whether I define into the page negative or positive, they will add. The only thing that I have to worry about is what is the distance between this and between the point and this wire, and the distance between the point and the other wire. So for this guy is D plus X, so D plus X, and this is D, and I'm interested in this distance here, so it will be D minus X, and you do the math, and you find the total magnetic field, and it's into the page. Okay, another quick example, a wire carrying current of that much in the direction shown. what's the resulting magnetic field 100 meters away from the wire. This is something, just mathematically correct, but maybe so especially if you have something like this. This is actually, this is something like a strike, a lightning strike. So a lightning strike will do something like this. Anyway, so again, the direction of the current is upwards, so that means the direction of the field here is in, and the direction of the field here is out, and then B is simply mu naught over 2 pi r, and you just do the calculations and you find what that is. Okay, all right. So the second thing is the going back to the finding the magnetic field using Biot-Savart law for another type. So all of this discussion up till now is basically the discussion related to the magnetic field due to a current carrying wire. So that's a long conductor, straight conductor. Another one is the magnetic field due to a circular loop. Again, we've done that in class, and we found that the magnetic field at this point here can be, after you do all the math, it can be found as this by this formula here, where the magnetic field is Bx only. The only one that is going to survive is Bx. Okay, so if x is equal to 0 somewhere here in the center of the loop, or in the center of the coil, or the loop in this case, so that means what? That means x is equal to 0, and then I have bx is equal to mu I over 2, not 2 pi, over 2, 1 over a, and a is the radius of the coil or the loop. If you have n of these guys next to each other, then you just multiply this by n. So if you have n of them, which is some coil of n turns, then you multiply by the number of coils n. So this is what it looks like. Okay, so 1 over a maximum here, and then it goes as 1 over a as you get away from the center. Okay, it's a bell shape like that. Okay, the second thing that we wanted to, next topic, which is Amperes law. Amperes law lets you evaluate the line integral along B over a closed circular path around the current carrying conductor. So if you have a current carrying conductor, a wire, and you wanted to calculate the magnetic field around that wire, you can use what's so-called Amperes law, where all you have to do is just if you have B over a closed loop, a ds, and this ds is simply a small segment, and you integrate it over the circumference, and the circumference is 2 pi r. If you do that, and you know what B is at this point is mu naught over 2 pi r, the 2 pi r will cancel with that, and so you find or you come up with what's known as Amperes law, where the magnetic field over a closed loop is equal to mu multiplied by I enclosed, the enclosed current in that loop. Now this is analogous, or not, it's not analogous, but it's, if you remember, it's something we've done something similar to this, where we've used Gauss's law, and there's a big difference between these two, where before we had a closed surface, so it was E dotted with dA, dotted with dA, and then we said it's equal to Q enclosed over epsilon naught, right? And then we have a closed surface, not line. Okay, here we have a line integral, here we have a surface integral, here we have the E, so I enclosed, here we have Q enclosed over epsilon. Here I have mu naught, which is permeability. So this will allow us to calculate the magnetic field due to any conductor as long as there is some symmetry. So we have three types of conductors, current carrying conductors, which are used in the applications. One is the wire, two is the solenoid, which is simply a coil or loops stacked next to each other, or a toroid, which is a donut shape that we'll see in a few minutes. So this is Amperes law. Amperes law just tells you that you can calculate the magnetic field using this formula, where you dot the B dot ds, and then it's equal to, over a closed loop, is equal to mu naught multiplied by the enclosed current. Okay, so I is the total current passes through the surface bounded by the closed loop. So if you have a if you have something like this, okay, and then you have three currents. One of them is positive in, one of them is out, one of them is in, one of them is out, out. Let's say if this is each one of them is 1, so it will be 1, 2, 3, 4, which is out. Minus 2 is in, so 4 minus 2, the enclosed current will be 2 amps in this case. So if this is my Amperian loop, and this is 1, 2, and these guys are in, so negative, and these 1, 2, 3, 4 out, currents out, so these are parallel lines, and then the net current or the enclosed current will be equal to 2 amps in this case. Due to current configuration with high symmetry, so something like a wire, something like a solenoid, something like a toroid. So there must be some sort of symmetry present. And the current passing through the loop is positive if the direction of the integration is the same as the direction of the using the right hand rule. Okay, so that means these two guys will have the same direction, so sine 0 is equal to 1. That's what it means. And if they are opposite direction, then the sine is equal, sorry, the cosine is 0. Sorry, the cosine of 0 is 1, or the cosine of 180 is minus. That's what he means here. So this will be 180, so minus, and these two guys, b is along ds, is positive. The integral will be positive. Okay. So again, if you have two currents, that will be simply I, the sum of these two guys in. So in this case, that's I1 is positive, and this is I2 is negative. So you just algebraic sum of the two. Let's start first of all by calculating in the first example, or the first application of Amperes law, is calculating the magnetic field using for a long conductor in the form of a cylinder. It's really all our wires are in this form. Now, if it is a thin wire, then R, the radius, is small, and then we will not care too much about the magnetic field inside. However, if it is comparable, it's a cylinder, then we have to worry about the magnetic field inside. Well, how do we do that? A cylindrical wire of radius R carries current R, which is uniformly distributed over the wire's cross-section. Calculate the magnetic field inside and outside. I would like to start by doing outside. So outside, what do I have to do? I first have to, let me just, we've done this in class, so I'm not going to worry too much about it. So the first thing that I have to construct an Amperian loop. This is my Amperian loop, okay? So if I'm inside that, this is my the radius of my Amperian loop, which is imaginary loop, right? So it will be R less than big R. If I'm outside, right, that if I am outside, let me just get the pen here again. Okay, if I'm outside, this will be my Amperian loop, which is outside that. Okay, so the first thing, if we do the actually, let me do the outside. If I do the outside first, then B dotted with ds, B is constant, and I need to know the angle between B and ds. If you look at ds, in this case here, at any point is this way, and my B is this way, so the angle between them is 0, and cosine 0 is 1. So I can definitely take this as to be BDS, and B comes out because it's uniform, and the only thing that I have to worry about is integrating the ds, which is simply 2 pi r. So the integral, the Amperian, the left-hand side of the Amperian formula is simply 2 pi r multiplied by B. The only challenge for me is to find what is the current, the enclosed current, because this is simply equal to, again, I'm going to get my pen, is equal to mu naught, right, and I enclosed. I have to know what I enclosed is. If I am outside here, the I enclosed is simply I. Okay, simply I. But if I am inside, then I have to worry about what is R, I is. So when I'm inside, so this is for R. This is for R less than big R. So I am somewhere here inside the wire. Then the enclosed I is simply I and multiplied by the ratio of the areas, the ratio of this area divided by the actual area, which is pi r squared divided by pi big R squared, and the pi's will cancel, and then I get I enclosed is equal to mu naught I, right, and r squared over r big R squared. If I put that in here for I enclosed, right, then I can do this. So my I enclosed this is equal to this here, okay, and you can see that one of the r's will cancel with this guy, the small r, and then I have this formula mu naught I over 2 pi multiplied by r. So it's linear. Remember, this is all constant, okay. Mu naught is constant, I is constant, 2 pi is constant, r squared is constant. So it's b is proportional to r, and r goes from 0 to big R. So r goes from 0 is less than small r is less than big R. Okay, that's what the formula looks like. Now, if I am outside, if my outside the wire, it's simply the I enclosed will just become I enclosed, and then for r bigger than r, mu naught is I enclosed, it's I, and then I can definitely simply take these guys in here, and then B is equal to the magnetic field outside is simply an mu naught I divided by 2 pi 1 over r, and this is exactly the same answer as we had before when we used Biot-Savart law for a long or for an infinite wire. So as you can see here, if I want to plot B as a function of R, when R is less than big R, small, the Amperian loop is less than big R, it's linear. It's 1 over, it's linear in R. So this is, okay, so this is constant, and I have B proportional to R. So that's a straight line. That's why you see the straight line here. However, here, when B is greater than R, when R is greater, let me just say, when R is greater than R, so that's outside, then it's 1 over R. So linear inside, the magnetic field is linear inside the wire, and when you go outside the wire, it's 1 over R. And with the maximum value, it happens when R is equal to R. Okay, that's the maximum magnetic field value. Okay? And we've done this in class. I think the only thing that you need to do in here is to, okay, so again, he wants the magnetic field somewhere inside. That's my Amperian loop. And the only thing that I have to worry about, the I enclosed, is something that I have to worry about, because he told me that the current is given by the current density, which is J is equal to CR squared. Now remember what J is. J is defined as I divided by A. Right, that's what J is. It's the I divided by A. So I will be simply, if you look at I, it's simply JA. So DI, or if I want to calculate I can integrate J dA. J is given by C square, C R square, and C is constant, some constant, R square, and dA, remember A is equal to 2, pi R square, okay? So if I want dA is equal to pi and 2R dr, and that's what dA is, okay? So simply dA is equal to 2 pi R dr, and if I put that in here, then I have R cubed over, R cubed dr from A to R, from this point here to, actually from this point here to there, and if I integrate that, I get, this is my I enclosed, and then B to R, in this case is the R is the Amperian loop, and you can calculate that. You can't do the rest of the math. This is the trick. The trick is actually in here, in finding what these 2 points here, what J is, and what A is and dA is. All right. So the last 2 examples, which is the magnetic field due to a solenoid, and a solenoid is nothing more than you have one loop, and it's stacked, or loops are stacked next to each other. So what we have to do, we have to calculate the magnetic field outside, inside, and outside. The way to do that using Amperes law is by simply selecting the Amperian loop to be some rectangle, and splitting it into four. So 1, 2, 3, 4. So this is let's see, segment number 1, segment number 2, segment number 3, segment number 4. And you notice that for segment number 2, number 3, remember I'm doing B dotted with DS. B is this direction. Now I showed you in class. If you're going in, right, that will be the current is in. That means the magnetic field is this way, and the current is out. The magnetic field again is this way. So the magnetic field in both cases inside the solenoid is this way. Now, if the magnetic field is this way and the DL or DS is this way, that means the angle between them is 90. So both 2 and 4 will give me 0 contributions. Okay, both 2 and 4 will give me 0 contributions. And for also number 3 will have no current enclosed. So that again will give me 0. And so the only contribution I'm going to have is from number 1, from segment number 1, which is BL. Right? DS is simply the length L, and that is equal to mu I enclosed. Okay, I enclosed is the current enclosed by that. Okay, so that's that. And then if I, of course, BL, that's is all BL is equal to mu. N is the number of turns, because remember, I enclosed for one loop. If I have n loops of them, then I have to multiply the enclosed current by capital N. So the magnetic field will be simply B equal to all of this divided by L. Usually it's written as something like this, divided by L, and this number is usually given as small n, which is the number of turns per unit length, as we can see here. So it's simply B, the magnetic field, is equal to that, where n is the number of turns per unit length. Now, as you can see here, the magnetic field, we just saw that the magnetic field outside is 0, and inside is it has some uniformity. If the solenoid is very long and you pick a region where you're somewhere in the middle, then you find this to become very closer to the maximum value, and it will be uniform. And that's what we'll be working with. We'll be working with very long solenoids. It's similar to what we did with the capacitor, where we actually stay away from the edges, so we look at only uniform, or we examine only uniform magnetic field. Last example is the toroid. And the toroid is what I call the donut. So it's simply the solenoid. It's the solenoid we just talked about, except now we connected the two sides. So we connected the two sides in such a way that it's a donut. Now what we wanted to do, we wanted to calculate the magnetic field at this point here, the magnetic field at this point here, and the magnetic field at this point here. Now, I don't want to, I didn't know if I mentioned this or not, but remember, the magnetic field here for the solenoid is 0, and non-zero, or uniform here, non-zero, and 0 here. So outside the magnetic field, or close to it, the magnetic field is 0, and inside the magnetic field is, this is if you're talking about a long solenoid. Now for the toroid, again, we have to use Amperes law. And Amperes law, the only thing that I have to do is just look at the I enclosed. Now there are 3 regions. If you take a region here with less than A, there is no I enclosed. So that's going to give me 0 I enclosed. If you take the region here, is also will give you 0 current. But why is that? So here it's understood that if I go less than B, there will be no magnetic field because there is no current enclosed here. But the question is, why is it when I go here, the enclosed current is also 0? Now, if you look here, if you take this to be in, this will be out on this side. And again, the current here is in, the current here is out. So when you add them up, remember we said the opposite direction currents, they cancel. So all the currents will cancel, and then we have again the I enclosed in this region is 0. So immediately I would say I can safely argue that the magnetic field here is 0. The magnetic field here is 0. The only thing that I need to know is the magnetic field at this point here. Okay, BDS, so that's simply the ds will be 2 pi r, is ds will be 2 pi r, that's my, so this is my ds, and the magnetic field, if you look at it, it's at the same direction as the ds, so that means the angle is 0, that means the cosine of the angle is 1, multiplied by that, and the total current is Ni, and of course multiplied by mu, so then I get my magnetic field inside the toroid is equal to mu and 1 over r. Remember, we have to show that the magnetic field inside the toroid, so this is from 0 to A, and this is B, and this is the, so the magnetic field here is something like this, and something, 0 here and 0 here. Okay, so 0 inside, 0 outside, and in here it's 1 over r. Okay, 1 over r, and that's it. So the magnetic field inside the toroid is not subject to the end effects, but not constant inside the okay, so okay, so if you look at this, this is what so this is what the it's 1 over r. It's not constant. That's that's what I'm trying here. It depends on r. Actually, depends on 1 over r. I shouldn't say r. It's 1 over r. Just a quick example here. If I have a thin 10 centimeter long solenoid, so that's L 0.01 0.1, and then N is equal to 400 turns. So that's N. And the current is 2, I can find the magnetic field inside near the center. Okay, near the center, that means it's very uniform, and that's what I mean. And that's it for the, just before I stop, this is a summary of the 3 types of, conductors. We have a line, conducting line or conductor carrying a current I in the form of a cylinder, which is wire, or we have a solenoid that carries a current this way, or have a toroid, which is a closed solenoid, or what I call the donut. And each one of them, there is a magnetic field inside. So this is linear inside. B is proportional to R. And then outside is 1 over r, so it will be something like this, and then it goes down. For the solenoid, it's 0 outside, and inside the solenoid it's equal to so the number, this is the number of turns. And again, the same thing for the toroid, is 0 here, 0 here, and inside it's 1 over r, and in here it's fairly uniform. Remember, it does not depend on r, depend in E or anything. L, of course, is we can get rid of it if we know what the number of turns per unit length. But this, for a long solenoid, the magnetic field inside is uniform. Okay, and that's it for the